So here we are, back again, and today we are going to continue our journey throughout the game Turing Complete. And yeah, now we are going to play the level The Maze, which is probably the first quite challenging programming level. The fabled maze. If you solve this, you win the competition. Write an algorithm that gets the robot from the start to the exit. This level is hard. You probably want to write down the pseudocode for your algorithm before you implement it. Use this hint if you get stuck. Let's see how long this takes. First of all, like the last time we were playing, we are going to define wait, how's this done again? Constant. Turn left. 0. Constant. Move. 1. Constant. Turn right. 2. Constant. Wait. 3. Constant. Shoot. 4. Constant. Shoot. This is action. Oops. Didn't mean to close this. Thankfully. I'm glad it's saved. Saved. So let's see if we are going to use now. If we are going to use the hint, I guess. Guess we won't. So here we are. So how do we solve this? First of all, we need a function that checks the fronts. That would mean input 2, 3. If greater 0, okay, first let me show you a thing. I already know this because I already played the game. So when we when we play the game, we see that we're seeing a wall, right? And just like in the last levels, we would be able to or we are able to read the input and see what it says. There's not only walls in this level, but there are also coins. Coins are 8s. And then there's an achievement. And this achievement lets you see now we should be 3 is the door. There's an achievement that you will get, respectively achieve, if you. Why is he facing the wall? He should be facing this side. That you unlock by collecting the coins. So, and there's that. Then we could maybe at some point write a code that collects the coins as well, but this makes the code quite a lot more complex, and the level is complex enough as it is. So we are first going to write the code that solves the program, that solves the level without collecting the coins, and move on from there. So if it is 0, that means if it is greater than 0, that means there's a wall. If it is 0, that means there's no wall. So here we would create a label, and sorry. Here we would create a label that jumps us to the function that, or insert a label. Let's write this down. To case wall. You would insert the name of a label that jumps us to a function that defines the action that we will have to take when we're facing a wall. So what do we want to do when we face a wall? Face wall. We might as well insert this label, right? So if there's no wall, we will probably just move forward. And then we would repeat. No, let's do it. Let's do it this way. For now. Label face wall. Okay. What happens if we face a wall? If we face a wall, we make another turn. Right? Okay, in general, the way we solve the level is we move a step forward if there's the possibility, then we check right. If there's a wall, we turn back forward and see if we can move forward. If the front is clear, we would repeat the process. Move forward and repeat the process. Right? So we would go forward, check if right is clear. If we can go right, we go right. Then we would turn back forward. And repeat the process. If the front is not clear, which is the case in, for example, right, let me show you with the mouse, right, in this corner, right, we wouldn't be able to go right. Then we would turn back forward again when we would face the wall. That would mean we would have to turn around. And then we would repeat. And that should solve the level. At least this code would get us to the wall. At some point in the code we would have to I'm not going to say this is phase wall. We're going to rename this. Check right. Turn around. So turn around is going to look like this. Turn left. R0 to out. R0 to out. Right? That's what turns us around. And we would face the free field again. So our condition in this case would be always loop. And we would jump back to the beginning of the loop. So this is turn around. Do we want to move forward? I guess so. So this is turn around. Check right. Turn right. R0 to out. Into R3. If it is not equal to 0, move forward. Because if it is not equal to 0, right, we wouldn't jump. As we turn around. So what if it is 0? And we'll move forward. And then we would loop always. And whenever we turn right, I will also use an action. see if there's a door. This is not correct. Check front. This is the next thing we do. And only if front is not clear, we would have to turn around. Yeah, we defined this. Check if front is clear. So here we just turned right? So we're facing right. So the first thing we do is turn left. A 0 to out. Then we would get an input. Put it into R3. Check if it is 0. If it is not 0, we will turn around. If it is 0, move forward, a 0 to out. Loop, always. So here we are. So in this case, we just turn around, move forward, and loop. So now, I would check right again. Does this solve the level? What is this? Okay, first of all, I'll delete this code. See if this works. Oh, why is it not? See, there's a bug. Let's see where we made a mistake. First of all, we might put some structure into this, right? That's the one we check if right is clear. Then we'll check if the front is clear. Turn around and repeat. Oh, we forgot to check if left is clear. Like, because in case right is not clear and the front is not clear, we would first check if left is clear before we would turn around. And this is basically the same as check if right is clear. But in this case we would turn left. We would have to turn left twice, right? In this case, since we're facing a wall on the right side. No, we check if the front is clear before we check if left is clear. Yes, this is correct. Then we check the left. So we turn left, see if there's a door. Then we would get our input. Yeah, that should solve it. And by the way, this is interesting. I told you about the ticks, right? This is we can fasten this, right? Because as you can see, this takes quite a while because it takes a lot of ticks. I don't know. Usually there is. Oh, there it is. So far we have 1,700. Now it's 800. 1,900 ticks. We can step this up, run faster, and this would be 10 kilohertz. And as I already told you in the previous videos, in one of my previous videos about this game, these ticks are measured in hertz. And if I'm not mistaken, just like on a real computer, right? If I'm not mistaken, 10 kilohertz is 10,000 ticks in a second, which you can also translate into gigahertz. Let's see, no, it's probably not 10,000 because it would be finished in an instant. So how does it translate? I'm not 100% sure. Hertz. Let us look it up. Why not? Sorry for not knowing this by heart. Hertz and ticks per second. Oh yes, it is. So this is just not equivalent to 10 kilohertz. It just is named 10 kilohertz. It is more like 1 kilohertz. If we look at this, 1, 2, 3, 4. Yes. I guess this ticks at 1 kilohertz. 1 tick per second. And 1,000 ticks per second. Oh wait, you passed the wall? Oh, because we didn't check for a door when turning back to the front. Unfortunate. What do we have now? See if there's a door. Copy this part. So where do we move it? Why does it want to check front? I mean, it works, right? So there's that. Anyways, once we check the front, would first turn left. Then would check if there's a door. Interesting. Anyways, this solves the level. Oh, now it is 10 kilohertz. No, it's not. The last level, it just felt like it was actually 10 kilohertz. Congratulations, you won the competition. An amazing achievement. Nice. If you choose to go on to the rest of the levels, I will teach you about RAM, the stack and function calls. And you will get to solve more interesting challenges like this one. But first, you would have to build a better computer. Overture was a good first machine, but it is clumsy and programs get very messy. To solve the challenge I have for you, without pulling all your hairs out, to solve the challenges I have for you, without pulling all your hairs out, you need something more expressive, the lag architecture, which is fun because when I first played the game, to solve the challenges I have for you without pulling all your hairs out, you will need something more expressive. The lag architecture, sorry, I butchered the sentence. The lag architecture. And this is fun. This is actually a joke, and I didn't get this when I was first playing this game. And yeah, what it is referring to is ARM, which is a very popular architecture. It is used for example in a Raspberry Pi. Let me see, I have one here. Maybe I can show you. Doesn't matter. Anyway, a Raspberry Pi is utilizing the ARM architecture as well as many mobile phones. So yeah, lag is a twist on this. It is a simpler version, and a very basic version. But yeah, we're gonna have a look at it. I hope you enjoyed the video, and we will continue our journey throughout the game. Goodbye. Oh wait, I'm gonna read this sentence before quitting this video. On the other hand, you could also retire. Be proud and enjoy your reward of not being eaten. Stats, the maze, architecture, level complete. Nice. So here we are. The next level is the XOR, which is probably a byte XOR, and the byte constant that we are going to examine and solve. But this time for real. Goodbye. Hope you had fun.